Welcome to this presentation. I'm Alireza Amiraghdam from the Visualization and Multimedia Lab of University of Zurich. In this video, I will present our locally adaptive line simplification algorithm called LOCALIS, which is mainly designed for visualizing geographic vector line data, but its application is not limited to this field. Vector line data is an abundant type of data in geographic datasets. The level of detail is usually managed by creating different versions of the dataset generalized at different levels. The shortcoming of this approach is that different levels of detail cannot be used side by side in one scene. In a 3D visualization, this shortcoming becomes critical because in many viewing angles, different levels of detail are required for different parts of the scene, depending on the distance to the camera. Otherwise, either the close parts will be too low in detail or the far parts will be too cluttered. Additionally, a large unnecessary data should be handled. To tackle this challenge, we have developed LOCALIS. LOCALIS simplifies lines non-uniformly, is based on a pixel-precise visualization technique for large vector line datasets, takes advantage of the GPU parallel computing power to run in real time, prevents unwanted intersections, and dynamically changes the thickness of the lines to reduce the clutter. I will explain each of these features starting with non-uniform line simplification. Our algorithm is based on Douglas-Poiker line simplification. For each line, we start with the most simplified version of the line. Then we add the point with the largest distance to the baseline. This distance is denoted as error. This point divides the line into two parts. For each part, we apply the same procedure, and in the end, we have a binary tree with nodes that represent points and their corresponding errors. After saturating the errors hierarchically, such that no node has a lower error than any of its descendants, we can simplify the line by pruning this tree while traversing it based on any given error threshold. Like this example, the error threshold can be a function of distance to the camera. Next, I will explain our pixel-precise 3D visualization of large line datasets. Recently, different vector rendering is introduced for visualizing large number of lines in 3D, which takes advantage of the power of GPU. LOCALIS uses the same concept. The color of each pixel is determined independently by comparing the distance of the pixel to the lines and the thickness of the lines. To limit the number of comparisons, an optimized search hierarchy is used composed of one grid and one quad tree in each cell of the grid. As a result, LOCALIS provides a pixel-precise rendering of large number of lines at any zoom level without using proxy data structures. Now I explain how we parallelized our algorithm to run efficiently on the GPU. Direct access to the vector data on GPU is a benefit. However, it is not possible to traverse trees redundantly for each pixel in real time. In order to make simplification possible in real time, we first create a set of all possible line segments that can emerge during the refinement process. The visibility of each of these line segments depends on 2 points. For example, this purple line segment will first appear when this green point is included. We call it generator, and will disappear as soon as this red point is included. We call it splitter. Storing all possible line segments with the generators and splitters as their attributes allows us to determine the visibility of line segments individually, which fits the parallel processing nature of GPUs. In order to have a valid line, no point should be included in the line when even one of its ancestors is excluded. In this example, the red point should not be included when the green point is excluded, or the green point must be included when the red point is included. This can happen when the error threshold is a function of distance to the camera and the ancestor is located farther from the camera. To solve this, we conservatively assume a lower distance to camera when validating the green point such that none of the points in the subtree can be possibly closer to the camera. The amount of this decrease is the maximum of distances between the green point and the points of the subtree and is denoted as Dmax. We calculate Dmax beforehand and store it with each point. For the same reason mentioned earlier, we also saturate Dmax. Lines can now be simplified non-uniformly based on an error function on GPU. In this example, we are using a lens that has a low error threshold inside and a large error threshold outside, thus high level of details inside and low level of details outside. The details are being added and removed to the line as the lens approaches and hovers over the line. In this example, the underlying set of all possible lines are also shown for demonstration purpose. Another challenge is to prevent intersections between lines when they are simplified. To solve this, we find all possible intersections. An intersection can happen when a point, such as B, is located in the triangle that excluding another point, such as A, creates. In this situation, excluding A before B results in an intersection. To prevent such intersections, we find all such dependencies and involve them in the saturation process of error and Dmax. As a result, no dependent point will be excluded before its dependees and no unwanted intersections will appear. These two examples show the unwanted intersections that can happen on the left and how LOCALIS prevents them on the right. The last feature I explain is dynamic line thickness. LOCALIS can dynamically change the thickness of the lines using a given function. This can be useful in wider viewing angles to keep the important types of lines visible while the others fade into the background. In summary, we get the lines as an input, create binary trees using the Douglas-Poiker algorithm, calculate error and Dmax values, find the intersection dependencies between lines, saturate error and Dmax values within trees and between intersection dependencies, and finally create a list of attributed points. At the same time, we create all possible line segments, find their generators and splitters, and create a list of attributed line segments. Then this data is loaded to GPU and rendered in the deferred vector map part of LOCALIS. During the rendering, simplification happens on the GPU and this data is not required to be updated. Now let's watch LOCALIS in action. In this test, we are visualizing the whole street data of Switzerland with 6.9 million line segments over a static train with all features of LOCALIS active. The performance ranges from 6 to 75 frames per second in this setup, which is indicated at the bottom at several points as we go on. LOCALIS increases the thickness of the important types of lines when zoomed out so only the important lines are visible. As we zoom in, other lines become visible gradually until they reach their actual thickness. By default, the error threshold is a function of the distance to the camera. Instead of bounding the error threshold to the distance from the camera, We can adjust the error metric manually, which causes all the lines to be simplified uniformly at the same time. We can also use a refinement lens. The error threshold inside the lens is low, which causes all the lines inside to be at their highest level of detail. The error threshold outside of the lens is high, so the lines outside are simplified as much as possible. We can see that the details of the lines adapt to the movement of the lens immediately. Since we use the deferred vector map rendering technique, the lines are always pixel precise no matter how much zoom we apply. If we visualize the underlying quadtrees, we can see the size of their nodes and how the line segments are distributed. The brighter nodes contain more line segments, and for the pixels inside these nodes, the GPU shaders have to do more distance to line comparisons to determine the color. This is the main reason why the performance is different at different zoom levels. We successfully implemented a real-time non-uniform simplification for vector lines in 3D by performing the operations directly on the attributed vector lines without using proxy data structures. The take-home message is that we can perform computationally intensive operations on vector data at render time on GPUs, which creates opportunities to increase the fidelity, flexibility, and responsiveness of the visualizations. Thank you very much for your attention.